Hello again, math analyzers. Here we are for chapter 5, lesson 3 notes. So we're going to multiply complex numbers, multiply regular imaginary numbers and complex numbers. So I just want to show you what the worksheet looks like just so you can see. I've got 2 examples over here that I'm just going to kind of walk you through. And then I'm going to tell you again that, we've got the graphing calculator that we can use for i's. It's so nice. Can't do it when we rationalize them. So when lesson 4 comes along, we won't be able to use it again. But for now, right, we've got the graphing calculator handy dandy. Got one right over here up here on my screen too, which I didn't use in the last video, but hey, whatever, right? Before I start, just a reminder of the cyclical powers of I, because this is going to be important when we multiply. If you multiply I times I, it's I squared. Well, I squared is equal to -1. And so that's something that's going to be a really big key is a lot of times when we're trying, we'll be purposefully trying to get a -1 or a +1 when we multiply i's together. When you have an odd exponent on your I, there will be an I left over. When you have an even exponent on your I, there will not be an I left over. See that? So that will be important if we multiply some i's together. Okay, multiply imaginary numbers together. Also, a quick reminder what we're talking about here that I, when I talk about it, I'm really referencing radical -1, the square root of -1, which we know we can't take the square root of. So that's whenever we have a negative number under the radical, this is the piece we pull out and represent as I so that we know this is a different piece than the rest of our pieces. Okay? Anyway, let's begin, right? So when you're multiplying, this is the same as multiplying radicals together because again, I just mentioned I really is a radical. So outside numbers multiply together, inside numbers multiply together. That's the way you want to think of it. So your coefficients multiply together, your i's multiply together. Whenever your i's multiply together, it's kind of like a variable, okay? You treat it as this is the same base, so you add the exponents, and then this simplifies. So that's why I gave you your cyclical powers of I again. Okay, that's the reason for revisiting these. Knowing these will help you when you get this that then needs to simplify. So -7i times 6i squared, well, -7 times 6, that's -42. I times I squared, that's I cubed. Well, -42 is really being multiplied by a -I because I cubed is -I. So that's what you replace it with, and you get 42. But remember, I showed you all that work. You can actually just plug this into your graphing calculator. So -7i times 6i squared. And there it is. Oh, yeah. There needed to be an I there. Good thing we did that, huh? Double checked. There did, because there was an I left over right there. So there it is. Now, also notice your final answer needs to be in A plus BI form. So in this case, there was not a coefficient that was added or subtracted, a real number added or subtracted in front of that 42i. In this case, there will be. And notice when I got this answer right here, I had to switch to make sure the real number was in front of the imaginary number. Okay, so that was something that I had to switch and make sure that was happening. So here, just like in regular multiplication, you distribute. So -3i times 4 is -12i. -3i times +5i is -15i squared. But what's I squared really equal to? -1. So this is -15 times -1, which is +15. And because that's your real number, because the I times I is I squared, and I squared is -1, that actually is now gone, and that's your real number in front. Okay. Again, that can be plugged into graphing calculator, so don't panic too much, right? There's just a couple of things. If I were you and doing this outright, like actually showing the work on your paper, I would go through the steps to make sure that I was getting it correct. Okay. But you can also use your graphing calculator. I always use my graphing calculator to double check because otherwise you'll end up with stuff like that. that you want to make sure you double check, right? Okay, so here we go. Let me just show you some done outright, right? And then some done in graphing calculator, just so we have an idea. Right here, 3i times negative 5i, that would be negative 15i squared. Well, what's I squared really equal to? Look back up, negative 1. So this is really negative 15 times negative 1, and it's really positive 15. And just to double check, make sure we are correct about that, 3i times negative 5i is positive 15. So right here, 2i squared times 6i times 3i cubed. 2 times 6 is 12. 12 times 3 is 36. I squared, I to the first, I to the third, they're all the same base, so add up their exponents. 2 plus 1 is 3, 3 plus 3 is 6. So I to the sixth power, what's it equivalent to in the cyclical powers? So the closest multiple of 4 without going over is 4. 6 minus 4 is 2. That means it's equivalent to I squared. And what do we know I squared to be? Negative 1. So 36 times negative 1 is negative 36. When it's an even exponent, an I will not remain. If it's an odd exponent, an I will remain. I'm just going to prove this to you in the graphing calculator. 2i squared times 6i times 3i cubed. There we go. Let me just go back and do number 2, just because this will give me a single BI form answer. So negative 4 times 8, that's negative 32. I squared times I cubed, that's an I to the fifth. Same base, add those exponents. 2 plus 3 is 5. Okay, so what's I to the fifth equivalent to? Well, the closest multiple of 4 without going over is 4. 5 minus 4 is 1. So I to the fifth is equivalent to I to the first power, which just means you get negative 32i as your final answer there. You should be able to plug this into your graphing calculator as well, but let me just prove it here first before I say that in for sure, right? There it is. So now I showed you how to do the distributing. So here I'll get 6i plus 10i squared. Well, I squared is really negative 1, right? So 10 times negative 1 is really negative 10, which is a number, a real number. So it's got to go first. And then the plus 6i has to go second because of BI form, A plus BI form, right? Again, plug in here just to be sure. Okay. Make sure. And again, make sure you've got A plus BI form. Okay. Now, this is when we get into the double distributing, the FOIL. If you've got two binomials multiplied together, it's 4 multiplications. So it's 2 times 4 is 8. 2 times 5i is plus 10i. 3i times 4 is plus 12i. Oh, those are like terms, so those will add up in the middle. 3i times 5i is positive 15i squared. Well, we already know I squared is equal to negative 1. So this is really a negative 15. Negative 15 plus 8 is negative 7. And 10i plus 12i is plus 22i. That should be my final answer. But again, I can go to my graphing calculator. So 2 plus 3i, times 4 plus 5i gives me negative 7 plus 22i. Okay. Last but certainly not least, and this one I cannot double check in my graphing calculator, but no worries, you're going to see something cool happen here. We can already tell, by the way, that these are same pieces with a different sign between them in the two binomials. So this is going to FOIL. This is a general form of something special, a word you know. All right, A times A is A squared. A times negative BI is negative ABI, right? They're all multiplied together. BI times A is positive ABI. Those are the same term and opposite signs and going to cancel. Oh, wonder what this is. And this is B times B is B squared. I times I is I squared. Wait, we know I squared is -1. So this is really just A squared minus B squared as my answer. Guess what these things are? Conjugates. Again, imaginary numbers are radicals. So they have conjugates as well. If you have two binomials with the same terms in them, but a different sign between them, and you multiply them together, the I terms have canceled out. They're the same term with different signs, they add up to 0. So you end up with just your numbers. So these numbers, you could square those and subtract them. That's how you get the answer for conjugates. Okay, so conjugates are still a thing with imaginary numbers. So you've got your complex number, its conjugate is the same pieces, opposite sign. So if my complex number is 2 minus 3i, its conjugate is 2 plus 3i. And when those FOIL, when those multiply together and FOIL, what you're really looking at is the square of the front one. I did something wrong on the front. I just want to correct it. This was a negative, and so negative here means positive. Add them up. Sorry about that. Let me move down. Add them up. Add up the squares. Because negative times positive times negative was negative here, then times negative. That's where the positive came into play. I pre-positived myself. Again, graphing calculator for help on these, right? But that's what ends up happening out here is because it's different signs. So this guy's negative, this integer in front is negative, but the I squared is a -1. So when those multiply together, you're adding those values, okay? So the imaginary number has canceled out, but a real number remains with conjugates. And this will again get used in the same way it got used last time in rationalizing denominators. Okay, this will get used again. But here, what we're just going to do is we're going to state conjugates or not conjugates, and then we're going to find our answers. Conjugates, how can I tell? Same pieces, different signs between. So this is conjugates. And all I need to do is square the front number. 3 squared is 9. Plus square the back number, right? 4 squared is 16. And 9 plus 16 is 25. That's going to be my answer with this. Let me prove it. The i's will have canceled out. 3 minus 4i times 3 plus 4i gives me 25. Those middle terms have canceled each other out. But notice right here on number 3, not conjugates, so that's not going to have anything cancel out, again, because it's not conjugates multiplying together. It's a binomial times itself. They don't have opposite signs. They have the same sign inside the binomials. So this ends up still having an imaginary unit as part of it, okay? So this is not conjugates. Tried to put my G before it belonged there, right? This is not conjugates. This is the same binomial times itself. So this is a FOIL problem, and the middle terms will not cancel. They will just add up. They will just increase in size. 5 is also not conjugates because those are not the same terms. They have different signs, but they're not the same terms. I would just use my graphing calculator for that one too. Okay, they're not conjugates on number 5. So 2 plus 3i times 4 minus 5i, 23 plus 2i. Yeah. Why make life more complicated than it is? That's why we have those graphing calculators. Oh, interesting on number 2. Is that conjugates? one sign change between the two, not both sign changes. This is still just FOIL these together. These are not conjugates on this one. So negative 13 minus 2i times 13 plus 2i. Yep. Okay. That's not conjugates. And my answer, negative 165 minus 52i. Conjugates. Haven't seen a pair in a while. And these are conjugates because only the middle sign is different between the two. So you can square the front. Negative 5 squared is 25. And square the back. 6 squared is 36. And add them up. 25 plus 36, 61. And just double check. There we go. Negative 5 plus 6i times negative 5 minus 6i, 61. This one is only letters, so the best you can do here is to FOIL. However, if you use my general form, you know what you're going to get is going to be x squared plus y squared. But let's just double check. Okay, so I know that this is going to be my answer from the general form I already have. But let's just FOIL double check. X times x is x squared. X times negative yi is negative xyi. Yi times x is positive xyi. So see, those have canceled out. They're the same term. They canceled out. Yi times negative yi is negative y squared, negative y squared times I squared. But I squared is negative 1, so negative 1 times negative y squared is the positive y squared. So I did end up with that after I FOILed. Conjugates. That's the general form of the conjugates. Let's look at our awesome comics because, man, oh man, that's the best part of chapter 5. Okay, anyone who's feeling like they can't handle the physics here should probably just leave now because I'm multiplying the wave function by its complex conjugate. That's right, just got real. There you go. Your poop emoji, if that helps. Because, again, wavelengths measured by these imaginary functions, complex conjugates. Cancels out that middle. Gotta love it. Down here, let's watch some TV. I think his name is Mathika. I think I just made an imaginary friend. Oh, that's her name. What? How do you know that he is imaginary? Because when I added him to his conjugate, he disappeared. Oh. His imaginary friend already left him. Guys, don't you love these comics? Come on, now you actually understand them based on all the stuff we're doing. I think you'll be okay with the homework, also short. We are to a point of a quiz, so we'll review and we'll quiz. This will be in Delta Math because, as you can see, we're not doing a ton of things that require a lot of work to be shown right now. So we'll make sure we have that in Delta Math. We'll review and we'll quiz. Guys, this has been lovely. I shall be seeing you. Bye.